Hello there. We are talking about graph neural networks. For newbies, GNNs are often confused with CNNs. Graph neural networks are often confused with convolutional neural networks. But in this video, we are going to talk about graph neural networks. So what I'm going to do is I'm going to give you a quick explanation of GNNs and how they relate to MLPs, CNNs, and also some examples of GNNs. And also I'm going to just quickly explain this Python code for graph neural networks. So what is GNNs? Graph neural networks is a type of neural network that is designed to work with graph data. Now, graph data is a structured data. So data points in a graph are not really independent, but they are connected together. That's why we have nodes in a graph. All right. That's why I even put these nodes here to to showcase that all data points in a graph, they are kind of connected. They are not independent. All right. So, like this picture shows, the graph consists of nodes and edges, and node features and edge features. Basically, nodes which are vertices rather, nodes represent entities, e.g., people in a social network like Facebook. Edges represent links. These are your edges. They represent links between nodes, which are basically, if you visit Facebook, we're looking at friendships in Facebook, right? Then we have node features, which is basically the metadata which describes each and every node. So what is this person? What is this person? Any metadata related to this particular node. Then we've got edge features, these lines. Basically, these are metadata data describing the connection between the nodes. All right, maybe this person and this person, they are connected by school. Maybe this person and this person, they are connected by location or maybe by interest, whatever it is. These are metadata describing connection between nodes. So why do we need to use GNNs? Now, normal neural networks such as multi-layer perceptrons, or MLPs in short, or CNNs, or convolutional neural networks, they really work with structured data such as grids, which are basically images, or sequential data, which are basically text. But graph data, as you can see from this image, is kind of non-standard data. The data is irregular, which means nodes or connectors or entities or vertices rather, they have variable numbers of neighbors, and the number of connections that they have, they really matter. So that's where really GNNs shines. Key idea here is that GNNs aggregate information from neighbors to compute a node representation. This is what we call kind of message passing. So basically, let's say in Facebook or any other social media platform out there, such as Facebook, such as TikTok, they use the data from your friends to recommend either content or other things to you based on the interests and likes of the people in your network. That's basically message passing. Basically, if a node represents a person in social media, their representation is updated based on their friends' features. Whatever the friends has, they have to push it towards you. All right. So I said GNNs, they have what we call message passing, and we also update node feature based on the neighbor's features or aggregated neighbor features rather. Then yeah, that's basically how it works. Well, of course, we have to repeat for several layers to propagate information across the graph. Common aggregations that we use in GNNs. We have your basic, mean, max. We have your sum, your average. Those are the most common ones, but there are also other advanced aggregations that we can use. Okay, so what are the most popular models under GNNs? We have graph convolutional network, GCNs. That's one of the more popular ones, which kind of uses normalized sums of neighbors. Whatever the summation of neighbors, it will pass to you. Then we have got graph sage, which aggregates neighbor features with any lend function, basically an algorithm. Then we have got a GAT or GAT or graph attention network, which uses attention weights to focus on important features. So it looks at all the features in your network, then it weighs them up and recommends or propagates it or pass it to you based on the weighting that it just scored. All right. So basically, I'm not going to go deep into this code because I'm going to come up with a hands-on, real-world, practical, hands-on code along video that will explain this in detail. But I'm going to give you a quick overview. So right here, I'm using PyTorch and I'm importing neural network. Then I'll just use it as F. Then I'm going to use a dataset from Planetoid, actually from Torch Geometric datasets, and the dataset that I'm going to use is Planetoid. Then I'm going also to import graph convolutional network. And I'm going to load my dataset. Then I'm going to define my GCN. Then also I'm going to train it. After training it, I'm going to evaluate it. After evaluating it, I'm going to check the accuracy, and I'm going to check the accuracy and print out the results. Basically, that's the structure. Wait for the full video where I can explain this in detail, but that's the structure. Like any other machine learning project that you're working on, you have, if you are importing data sets, you have to import your data sets, your necessary modules, you train your module, you evaluate your module, and check the result. All right, thanks for watching. See you on the other side.